A large part of physics is centered on completely understanding forces, and bosons are crucial for them to operate. The currently known forces are as follows: gravitational, electromagnetic, weak nuclear, and strong nuclear. When referred to in physics, bosons relate to these four fundamental forces. The most notable bosons are as follows: the Higgs, the gluon, the photon, and the W or Z bosons. For simplicity, I'm mainly going to consider the photon, gluon, and W or Z bosons and how they relate to three of the fundamental forces in this video. So let's begin then by talking about the strong nuclear force first. It operates using a process that utilizes a boson called a gluon, but there is a property that gluons and quarks have that isn't found anywhere else in physics: color. It's important to note here that color is not like we perceive it, it's just a property that physicists use to describe these quarks and gluons. So as it turns out, the exchange of color of the gluons with each of the different up and down quarks is what creates this extremely strong force. Since there are so many protons in the nucleus of an atom, it would make perfect sense for one to hypothesize that all the protons would fly apart from each other because of the repulsive electromagnetic force. However, this strong nuclear force overcomes all of this repulsion and keeps those protons together in every single atom. Onto the weak nuclear force. It's mainly responsible for the radioactive decay of matter. For example, the weak nuclear force facilitates how carbon can turn into nitrogen through the decay of a neutron of a carbon atom into a proton. You might ask why this could happen out of seemingly nothing, but the answer is simple: W boson interaction. When a W plus boson interacts with the down quarks of a neutron, it changes it into a proton by changing one of the three down quarks of a neutron into an up quark. This changes the quark composition of that particular neutron from being a down-down-up into an up-up-down, resulting in a +1 charge for that subatomic particle.
What Jason described is actually a charged current interaction involving the W plus boson represented by this Feynman diagram. In particle physics, these kind of diagrams are the standard way to depict particle interactions amongst all fundamental particles. Like what Jason said, this diagram shows that when the neutron and neutrino approach each other, a W plus boson is mediated between the two that causes the neutron to turn into a proton and the neutrino to turn into an electron. On the flip side, another weak interaction that is actually a more accurate description of the nuclear decay of a neutron from carbon-14 involves the W minus boson. A down quark from a neutron emits a W minus boson and subsequently turns into an up quark, changing the neutron into a proton, and the W minus boson ultimately decays into an antineutrino and an electron, and this is the Feynman diagram of this interaction. Although the Z boson is not involved in interactions that change the flavors of quarks, the Z boson facilitates what is known as neutral current interactions such as neutrino-electron scattering. These kind of interactions are ultimately significant for understanding the big picture of the interconnectedness between the weak nuclear and electromagnetic forces.
Now on to the Higgs boson. The Higgs field emits countless Higgs bosons that come into contact with matter. Different particles interact with the Higgs field to give this matter more or less mass with respect to how much these particles actually interact with the Higgs field. One important warning for the Higgs boson to consider is that the Higgs field doesn't actually facilitate gravity, though that is just a property of mass that isn't directly related to the Higgs field. Finally, we have the photon. First off, the photon is considered to have both a particle and wave duality. This means that it can either act like a wave or a particle, just depending on whether or not someone is observing it. In the context of particle physics, just realize that the annihilation of matter and antimatter, like an electron and positron pair, can release energy in the form of photons. The photon is referred to as a carrier particle, meaning that it is responsible of mediating the behavior of electrons that govern the electromagnetic force. Just remember, the entire reason that you're able to watch this video right now is because of the photon. When discussing the gravitational force, we have to address the graviton, the boson theorized to be responsible for gravity. However, as of today, in the year of 2016, the graviton has not been discovered by the scientific community. Therefore, the graviton is currently a missing piece in the standard model of particle physics. Ultimately, the discovery of the graviton in the future will make the standard model more complete, to a point where it can individually explain all of the four fundamental forces of nature.
But as of right now, it's not that big of a deal that the graviton has not been discovered. It's important to know that the effects of gravity are very minuscule in most particle interactions. And on this note, let's see how well you paid attention. Can you list the 4 fundamental forces from strongest to weakest based on this video? Feel free to pause this video for a moment to figure out the answer, and also feel free to re-watch some parts of this video as necessary. If you already know the answer, then feel free to carry on with the rest of your day. If you answered strong nuclear, electromagnetic, weak nuclear, and gravitational, then give yourself a pat on the back. Hope you liked everything, and if you want to learn more about particle physics in short and sweet videos like this one, check out more of our videos on our channel. Thanks for watching, and see you again next time.